Hello. Hello. Am I audible?
Yes, ma'am. Good evening.
Good evening. Okay. And my screen is also visible?
Yes, ma'am.
Okay. So I'll just wait for 2 minutes and we'll start after that. Like we'll wait for more people to join. So we'll start at 7503.
And perfect matching.
Yes. Yeah.
That perfect matching. It is a one factor, ma'am. One factor matching.
Yes. One factor. So we'll define these. Okay. So I'll begin. My screen is visible, right? Hello.
Yes, ma'am.
Okay. So, I good evening, everyone. I welcome you to the fifth problem solving session of NPTEL course Graph Theory. So today we'll be discussing perfect matching and stable matching. So first, I'll recall the definition of matching. Matching, we did this in the last tutorial also. So matching is any subset of edges such that every vertex is incident to at most one edge in N. and and by matching is we are looking at some special subsets of some special subset of edges, and every vertex can be incident to at most one edge. And perfect matching is a matching which consists of all the vertices of G. That is, every vertex is adjacent, every vertex is incident to exactly one edge in the match in that subset N. So matching is also what is called a one factor. So what is a K factor? K factor is a K regular subgraph of G containing all vertices of G. It is also referred as K regular spanning graph. That means basically K regular means that every vertex should have degree K, and spanning means that that subgraph should have all the vertices of G. And if we are talking about one factor means we are talking about one regular graph. So that means every vertex has is incident to exactly one edge, and there that is the definition of matching. And it is also and since it is spanning, that means it should consist of all the vertices, therefore it is a perfect matching. So a one factor is a perfect matching. And similarly you can see two factors. So so if a graph is too regular, can you say something about it? If a graph is too regular, can you say something about it, that what kind of graph it will be?
It is a bipartite graph.
Not necessarily. Bipartite graphs are need not be too regular. Too regular means that every vertex will have degree 2. So there can be a bipartite graph in which a vertex has degree more than 2 or less than 2, isn't it? So what kind of graphs are, what are two regular graphs? So you can see that two regular graphs, if you are talking about two regular graphs, they will be disjoint union of cycles. Of cycles. And if we are saying two factor, that means we want some disjoint union of cycles which is covering all the vertices of G. So let's understand this k factor with some example. So in the left you can see this is a bipartite graph, and by k factor we means that we require a perfect matching. So a perfect matching is basically set of edges such that every vertex is incident to exactly one edge. So you can see the shaded yellow and shaded yellow edges, like these three edges. If I'm naming them A, B, C, D, E, F. So yellow, this refers to edges A, B, C, D, E, F. This is a one factor or a perfect matching because first of all it is covering all the vertices in the graph, and secondly each vertex is incident to exactly one edge. And similarly you can see that orange edges are also forming a one factor, which is AD, CF and BE. So this was one factor. Now if we look at this example, this is a, so by two factor we means we want to find a regular two regular graph two regular graph which is spanning all the vertices. So you can see if we look at these two cycles A B and C D E F G H. If we just look at this graph, basically if we look at this following if you look at this following subgraph which has just these two squares, so this graph is two regular and also it is covering all the vertices of G. So this subgraph H is a two factor of this graph. So does everyone understand what we mean by K factor? Is there any doubts in the definition of K factor or two? If not, in the second example, can you give me some other example of two factor? Can you find any other two factor in the second graph? Other than H, other than H, can you give me another two factor in this graph G2?
No, madam.
Why? I am saying there is another two factor. In fact, there are many two factors. Just give me one more. So by two factor we means we have to find a two regular subgraph, or as I'm saying, two regular graph is basically disjoint union of cycles. So in this graph you have to find disjoint union of cycles which is covering all the vertices of, which is having all the vertices of G2. Basically disjoint union of two cycles, and there are 8 vertices, so all the 8 vertices are there. So one is that we can take one as ABCD as one cycle, EFGH is one cycle. These two cycles are disjoint and therefore it forms a two factor. So can you give me another example of a two factor in this graph?
B, C, D, F,
AEH,
Sorry?
D,
D,
So yeah,
D,
yeah.
C,
A, AEHD.
A, B, uh,
Yes, ma'am. ABFE,
A, B, F, E. Okay, good. And
DCGH.
A, B, F, E and D, C, G, H. Yes. So his example is basically H prime is this. So this is a this is a regular 2 subgraph, and it is having all the vertices. So, therefore, this is also a 2 factor of this graph. And similarly, now you have got this one. Similarly, you can see there are other 2 factors also. You can take this, you can take any other things like this, any other things like this to get many 2 factors in this graph. Now, what about this? Is it a 2 factor? If I take this subgraph EH, and if I take this, if I take this subgraph, is this a 2 factor?
No, man.
Because EH is not a cycle, ma'am.
Yes, because the vertices E and H have degree 1. So this is not a 2 regular subgraph. Therefore, it cannot be a 2 factor. Okay. So this was about K factor. Now, in the last tutorial, we see that we have a nice necessary and sufficient we had a nice necessary and sufficient condition to ensure whether a bipartite graph has a perfect matching or not. Now, that was Hall's theorem. So today's theorem is also something like this. It is basically giving us a nice necessary and sufficient condition to show whether a graph will have a perfect matching or not. And the theorem exactly says the following, that a graph G, the graph G will have a perfect matching if and only if we look at any subset S of vertices, and if we remove those vertices from the graph, then the induced graph that we get, number of connected odd components should be less than equal to number of connected odd components should be, oh sorry, this should be S should be greater than equal to, number of connected odd components should be less than equal to the order of S. So this is the condition of today's theorem. So now, did you so C or G minus S is refers to the number of odd components, and components we means that maximal connected subgraph of G. So now we'll see. So now this is a necessary and sufficient condition. So if we have to show that some graph does not have a perfect matching, what we have to do, we find S of suppose k vertices such that its removal is giving us more than k components. So suppose if we have this graph G is this one which has these many vertices. So first let's try to see if it has perfect matching or not. Let's try to compute for something. So what if I take my S to be F, what is C odd G minus S for this? So basically if I remove F, how many odd components do I get? If I remove F, how many odd components do I get?
Odd component means
One.
we have to count the vertices.
Odd components is basically, so if you remove F, if you are removing F, the resultant graph will have some components. Basically every graph has component, so you have to count the number of odd components.
Yes, one.
So yes, so
One component.
yes, so if we take S to be F, if we remove F, then the graph remains connected. And how many vertices do we have? 1 2 3 4 5 6 7 8. So we just get one component for this. What about if we remove D and B? How many odd components are we getting if we remove D and B? So if I remove D and B, my resultant graph will be like this. I am removing D and B, so my resultant graph is this: E G H F. So how many odd components do we have here? After removal of D and B. So my resultant graph is this. If I remove D and B, so how many odd components do this graph have now? Just one?
One man.
Just one.
One. Yes.
So this is also not.
Madam, you said D also to be removed, na?
Oh, I'm sorry. I removed D. We have to remove D also. Okay. Yeah. So if we remove D, okay. If we remove D and B, then we are getting this. Yes. Sorry. Huh. Now if we are removing D and B, so these two edges are also not there. So now how many odd components we have? In this graph, if we are removing D and B, how many odd components do we have?
Two.
2. So we remove 2 and we are getting 2 odd
No,
components.
ma'am, we are getting three, ma'am.
Why?
A is also a component.
Yes, so this A is a component, F is a component, but this is a even component because it has even number of vertices. We have to count only the odd components.
So we have two. Okay.
Yes, yes. Uh, so now you'll see that if you remove any of these, you won't be satisfied, be able to satisfy this condition. So I like you'll have to check for more. But I now if I say that this graph has a so we checked for few. Now since we are getting that this is satisfying the condition, let's see if we can find a perfect matching. So can you think of some perfect matching in this graph? G. So this G has a like can you find a perfect matching in G, or whether this graph G has a perfect matching or not? This graph.
No man. Perfect.
So if you are saying that this graph has no perfect matching, then you'll have to give me a set of k vertices such that its removal is giving us more than k odd components. So I'm right now I'm saying it can have perfect matching, cannot have perfect matching. So what do you think? Does this graph has a perfect matching or not?
If we remove G also, then
Okay. DB and G. You're saying DB and G?
yes, ma'am.
So if we remove G, then this is the graph, right? So how many odd if you take S to be D B G, then how many odd components you are getting? 3, right? So this is also not giving that condition. So if a graph does not have a perfect matching, then we should be able to find some vertices, k vertices, such that whose removal is giving us more than k odd components.
CB.
So you are saying CB, remove CB. Okay, let's see if we remove CB. If we remove CB, then the resultant graph is, if we remove CB, then we have this. The resultant graph is, okay, where is no C. E, F, G, H. There is no C and AD. So this is the graph, right? If oh, okay, there is no C.
No,
So
no, B.
so this, so this is the graph, right? If we remove C and B, so how many odd components it has? If we take S to be
Two.
CB, number of odd components are 2, right? This one
Yes.
and this one. So this will also not help. This is also not helping. So maybe since we are not able to find any set, let's see if we can find a perfect matching. So this has 8 vertices. You have, if it has perfect matching, we should be able to find 4 edges, 4 disjoint edges. Can we find them? I'm saying let's try.
Yes, ma'am. FB,
Yes, okay. So your edges are
FB,
FB,
AB, sorry, AD,
AD,
WC,
WC,
EG.
EG. Good. So see, he has found a perfect matching. Therefore, therefore this graph have a perfect matching. So no matter whatever set of vertices you will pick, you the number of odd components after its removal will be. So if you are picking k vertices, since this graph has a perfect matching, if you pick k vertices, then its removal will give you less than equal to k odd components. So does everyone understand this? Why this graph has a perfect matching and the statement of the theorem also.
But ma'am, in that we are not able to find out C odd G minus S.
So today's theorem says that if the graph has perfect matching, and if you remove k vertices, the number of odd components after the removal will be less than equal to k, and this is a necessary and sufficient condition.
So
So if
they,
you so if
we
you
have so ma'am, we have drawn four components, yellow one. So there are four components. Now, what is the set for this?
as no, when you have perfect matching, then you don't apply the so then you won't get a set. So the theorem, if you have perfect matching, then you won't get a special set S. But if the graph does not have a perfect matching, then you will able to find some set of k vertices whose removal will give more than k components, more than k odd components. But if a graph has perfect matching, then no matter whatever set you will pick, the number of odd components will be less than equal to the number of vertices. Did you understand the theorem? Is this was your doubt?
Yes, that is why the equality sign is coming for the turtle theorem.
Yes, less than equal to, yeah.
No, no, but we have tried now four, five examples in
Yes.
which we are getting C or G minus S is equal to S.
Huh. In our example, we are getting this, but it can be less than equal. It can be less than also. If it
Can
is,
we, so
if it
can we
is,
say,
hmm?
so can we say if G minus C or G minus S is equal to S, so then it is a perfect matching? Can we say like this?
So if it, see, if it is happening for all the s's, then it has a perfect matching because it is a but the theorem is saying that even if the number of odd components are less than equal to s, then also it is a perfect, it will have a perfect matching. The problem arises, the graph won't have a perfect matching if the number of odd components are than the greater than the order of s. If they are less than equal to order s, then we are fine.
Okay.
Okay. Now in the second example, what do you think? Is the second example, do the second example has perfect matching?
No, ma'am. If I remove vertices
No.
number one,
Why?
if I remove number vertices number one,
Sorry, you are not very audible. What?
remove vertice number one.
Yes.
If I
Yes.
remove vertice number one,
If we remove vertex number 1, yes, so how many odd components are we getting?
I think two, ma'am.
Yes, because if we remove 1, then the resultant graph is this. And we have two odd components. G minus S is equal to 2. So the condition for Tooth's theorem is not satisfied. Therefore, we can say that this has no perfect matching. So these two examples clear to everyone? Any doubts in this and the statement of Tooth's theorem? Okay. So if it is clear, let's let's move on to some questions. So now I told you what is a one factor, what is a what is a one factor, two factor, and three, like what is a k factor. So what do you think? Does this graph has a one factor? And if it has a one factor, tell me a one factor. So what do you so one factor is a perfect matching. So basically this graph has 10 vertices. So you have to find 5 disjoint edges. If it has a one factor, that means it has a perfect matching. So does this graph has a perfect matching? If it has a perfect matching, then we have found our one factor. So think about this. So what do you think? Does this graph have a perfect matching or not? Do this graph have a perfect matching or not?
I think matching exists, ma'am.
Sorry. So you are saying it has a perfect matching?
Yes, ma'am.
Okay. So can you give me an example? Can you tell the edges?
AB,
A, B.
AG,
Okay.
then EF,
Okay.
HJ,
Hmm.
GI,
G, I,
and then DC.
D, C. Okay. So, so, so yes, this is a perfect matching. So, Kashi, were you saying the same example, or you had a different matching? You had a different one factor?
Yes, ma'am. But okay.
Okay, so there's one more ACDG. ACDG. So somebody commented. Let me see. ACDG FHJBIC. ACDG FHJB and IC. Yes, that is also a perfect matching. So this graph has a one factor. So that is true. Now what about a two factor? Does this graph have a two factor? So what do you think? Does this graph have a two factor? So two factor, as I said, two factor means that we have to find.
Yes, ma'am. Two factor.
Okay, so first two factor means two regular spanning graph. So that means we have to find, and two regular subgraph looks like basically cycles. All two regular graphs are disjoint union of cycles. So if we have to find a two factor, we have to find if
Ma'am,
we
inner square and outer square, can we say?
no.
No, no. In that C, in that C and J is also there in inner.
Ma'am.
Yes, yes, that is
A
right.
A C
Yes, okay. So there is one A, yeah,
C D
ACD.
FGHI.
So you are saying ACD.
Yes, ma'am.
Ma'am,
A.
you write A B C D.
Okay, first of all, let him speak, then I'll come to your example, Anupam. Huh. So, yes, what is your example?
ACD.
But ACD is not a cycle, right? ACD,
Ma'am, yes. Sorry, AED.
AED. Okay, yes. You're
Sorry,
saying,
sorry.
ha ha
I
ha.
think
Okay,
C.
that it looked like C. Sorry. Okay. So you are saying AED. Okay. Then,
Yes, ma'am.
hmm,
FGHI.
FGHI. Okay.
BJC.
BJC. Yes, perfectly right. This is also right. This is a two factor because it is covering all the vertices. It is covering all the vertices and each vertex has degree 2. So,
Ma'am, I will give you a simple factor, ma'am.
okay.
A B C D,
A,
that
B, C, D. Okay.
then inner hexagon.
Okay. Yeah, that is also a two factor. Yes, that is also a two factor because all the vertices have degree 2. All the vertices have degree 2. Okay, so this was simple. Finding one factor and two factor. What do you think? Does this graph has a three factor now? So if this graph has a three factor, that means we should be able to find a three regular spanning graph. Each vertex should have degree 3. Each vertex should have degree 3 in that subgraph.
Yes, ma'am.
Okay. So you have found the.
Yes,
Okay. So what is your example? Wait,
ma'am.
wait,
AF.
wait. I'll just copy this image once because. Yes. So what is your example?
No, no, one vertex is missing.
D. Okay. Yes. What is your example? So you were saying somebody was saying some example. Okay. So maybe so in this find a three factor. That means three regular subgraph which is uh, which is containing all the vertices. So for particularly for this graph, I have a hint. How to find a three factor? I have a hint. This given graph G, you can see, is a four regular graph. That is, each vertex has degree 3 in this, each vertex has degree 4 in this graph. So now if you have to give me a three regular graph, that means you have to just remove one edge for each vertex. So what do you think? Does this graph has a three factor? That is H subgraph of G. H is a subgraph of G such that H is 3 regular and vertices of H is same as vertices of G. So does everyone understand the meaning of regular three regular graph, or basically three factor? So what do you think? Will this graph has a three factor?
Ma'am, it has a three factor graph.
Okay. What is the graph? What is the subgraph then? If it has a three factor, then you have to give a three factor. What is the three factor in this graph?
As you said, we have to remove one edge, na ma'am.
Yes.
One edge. So we will remove AD edge.
ADH as in
We have to remove that. So
AD.
then,
You remove AD edge.
no. AD edge.
AD edge. Okay. And so what you
Then we remove GF.
AD, sorry, if you remove AD, GF.
Yes.
Okay.
Then you remove IC.
Okay. Then
Then you remove JI.
okay, but if you'll remove JI, if you'll remove JI, then degree of I will be 2, right? But you in the if you are removing IJ also, then degree of I will be 2, right?
Yes, yes.
So you can't remove IJ.
You
So
can remove,
basically
ma'am.
you cannot remove two edges which have a common vertex.
Ma'am, you can BC. You can remove B and C.
Okay, if we remove BC, no, if we are removing BC, then C will have degree 2 because BC and IJ are sharing a BC and CI are sharing a vertex, right? So in the graph, if we are removing CI and BC, then degree of C cannot be 3. It has only 2 adjacent vertices left. So you cannot remove BC also if you have removed these 3.
So,
So you see, so in this example, we can see that,
ma'am, can we in with the symmetry? Can we remove IH?
okay, so
Uh,
somebody said BJ. Yes, we can remove BJ for now. And yes, there's a comment, can we remove only the yellow lines? So there is a comment which is saying, so first of all, in this example, if we are removing BJ, that is correct. So we cannot remove BC. Okay, where is the example? We cannot remove BC. Then there's a comment which says remove BJ. Yes, we can remove BJ for now because this is this. But still, we haven't removed 5 edges. And then Sundar is commenting that we can remove all the yellow edges. So what do you think? If we remove all the yellow edges, will the resultant graph be 3 regular? So if we are removing yellow edges, will the resultant graph be 3 regular? So in the yellow was one factor. So in that graph, every vertex has degree 1. Now if we
if we remove yellow, then it will be three factor graph.
3 factor graph, why?
And every node is having then degree three.
Degree 3. Yes, because one, so basically if we have a 4 regular graph and we are removing a 1 factor, then we are getting a 3 factor, because earlier every vertex has degree 4. Now in one factor every vertex has degree 1. So if we remove the edges of one factor, all the in the resultant graph, all the vertices will have degree 3. So we get a 3 factor. So you can see, if we have a one in our 4 regular graph, if we have a 1 factor, then the complement of it is giving us a 3 factor. So there were very many so when we were discussing one factor in this graph, we had three, we got 3 examples. So complement of those in this graph will give us 3 factors. So is this question clear to everyone? So we see that this graph has both, has also 1 factor, 2 factor and 3 factor. So is this question clear to everyone?
Yes, ma'am. Yes, ma'am.
Okay. So now these are simple true false questions. So first is that if G has an odd component, G can't have perfect matching. True or false? So G is a graph. Need no
It
G.
is a true, ma'am. It is a true.
Okay, so you are saying it is true. Why it is true?
Ma'am, we can take example of triangle, and then it has a odd component, but it doesn't have perfect matching.
Yes, but if you are saying it is true, then it should work for every graph which has an odd component.
But ma'am, for the triangle, if we prove that, so
So okay, so yes, you are right. So why it is working for triangle? What is the reason it is working for triangle? Then you can give the same reason for.
odd cycle, ma'am, odd cycle.
Okay,
It has a C3 is a odd cycle. So if we take C5, then again it will not work.
but there can be an odd component which is not an odd cycle. There can be more. There can be a component which is not an odd cycle but has odd vertices. Then suppose G has 2n plus 1 edges. Suppose, so if G sorry 2n plus 1 vertices. So if G has an odd component, if G has an odd component, then this implies that G has a component of 2n plus 1 vertices. So if a graph has odd number of vertices, can that graph have a perfect matching?
No,
Why it cannot have perfect matching?
because ma'am, it always it will leave one single edge with 1 degree.
Yes, true. So because in perfect matching we have to find disjoint edges, we have to find disjoint edges which are covering all the vertices, and each edge is covering 2 vertices. So if a graph has 2n plus 1 vertices, we cannot have a matching with more than n edges, because after n edges, if we have to cover the leftover vertex, we have to cover it with a vertex which has already been matched. So if G has an odd component, G can never have a perfect matching. So does everyone understand why is it true? Okay, so what about second? If G has an isolated vertex, G can't have perfect matching. True or false?
True, ma'am.
Why?
The isolated vertex, if it is, then it has 0 degree, ma'am.
Yes, and we cannot cover an isolated vertex, because in matching we should be able to find a edge. Every vertex should have exactly one edge adjust incident to it, but for that isolated vertex we won't be able to find any edge. And Third is Kn has perfect matching for all n, where Kn is complete graph on n vertices. So do you think it is true or false?
Ma'am, if n is even,
Hmm.
then it is true.
Okay. So if n is even, it
Then it
is
is true, ma'am.
true. But if k is odd, then it is not true, because we already see that if G has odd number of vertices, then if G has odd number of vertices, then it cannot have a perfect matching. So are all these three statements clear to everyone? Okay. Now the next question is G bipartite? Is this given graph bipartite? And if yes, we have to find the and sorry, if G is bipartite, and secondly we have to find the maximum matching in G. So this graph has 9 vertices. If this graph is bipartite, then we should be able to find A, B disjoint sets of A and B such that order A plus order B is equal to 9. So if this graph is bipartite, we should be able to find this. And if this graph is not bipartite, then we should be able to find a odd cycle. Because we have this theorem that G is bipartite if and only if it has no G is bipartite if and only if it has no odd cycles.
Exactly.
So what do you think? Is this given graph bipartite or not? And if it is bipartite, you should be able to give two independent sets. Two disjoint independent set whose sum is equal, whose order sum up to be 9.
Ma'am, it is bipartite graph, ma'am.
Ma'am, it is bipartite graph.
Okay,
So,
okay,
so
okay,
can I
okay.
give you that, ma'am?
No, Vinegam said it first. So he said it is bipartite. So what are the bipartitions then if it is bipartite?
Ma'am, it has odd cycle, ma'am. So it is bipartite, ma'am.
What is the cycle? It so see, G is bipartite.
Ma'am, can I give you the set of the two sets?
I'll ask you. G is bipartite if and only if it has no odd cycles. So if it has an odd cycle, it cannot be bipartite. So what were you saying? So if is this graph bipartite or not? So Anupam is saying it is bipartite. Any others? Vinigam, what were you saying?
Madam,
Yes.
graph is bipartite if and only if it has no odd cycle, ma'am.
Yes.
So,
Yes.
so this graph is not a bipartite, ma'am, because it has a odd cycle.
What is the odd cycle? Which odd cycle you're talking about? So you have to give me an odd cycle if you are saying it is not bipartite. So odd cycle means cycle with odd number of edges.
Yes, ma'am.
So what is the odd cycle in this graph?
D I G D
D I D I,
G D of
but
length 3, ma'am.
IG is not an edge.
Why, ma'am?
IH is an edge and IHG is an edge. IG is not an edge. This is
Ma'am, ma'am, I will give you the set of
wait.
bipartite first.
Okay, okay. You will. So wait. So did you? IG is not an edge. Did you get this? So it is basically IH is an edge, HG is an edge. IG, it is a path. There are two edges. It is not an edge. Is this clear? Okay. So DIG is not the cycle here because there is no edge between I and G. Okay, Anupam, so you were saying that it is a bipartite graph. So what are the bipartitions?
Ma'am, one is 6. So
Hmm.
A, E, I, G, and C.
AEIGC. Okay. And B is the leftover vertices, right?
Yes, ma'am. Yes, ma'am.
Uh, so what is this? So A, E, C, G, I. And the other set is,
Leftover set is
yes. So D. So everyone agrees that this is a these two are independent set. That means there should if if A and B are independent, that means there should be no edge between the yellow vertices and there should be no edge between the purple vertices. And Vivek has also answered this and he has also given the same set. So, yes. So, we see that since we are able to find two bipartitions, two independent sets like this graph is bipartite. And one set, this graph is bipartite and one set has AEIGC.
1 5 1 4. So that it is not perfect matching, but we will get matching up to 4, ma'am.
Okay, wait. So, then there's this next question. Yeah. So, DHFB. So first is does this graph has a perfect matching?
No, ma'am. No.
No, because it has odd number of vertices. So this graph cannot have a perfect matching. But what is the largest size of matching it can have?
4, ma'am.
4. So if it has a maximum, so 4. So does it have a matching with 4 edges? So now if you know the answer, just raise your hand. Don't answer it right away. So since this has 9 vertices and it is a bipartite graph in which one bipartition has 5 vertices, second bipartition has 4 vertices, this graph can have matching of size at maximum 4. So does this graph has a matching of size 4? Yes or no? Yes. Okay. So there's an answer yes. Now if the answer is yes, then we should be able to give the edges. Okay, so there are another yes also. Okay, so now if it has perfect matching, so one of you can speak up the uh, the matching. So what are the edges? Okay, so Anupam Sundar, any one of you can answer this. You are saying that it has a matching of size 4. So what is the matching in this graph of size 4? That means you have to give me 4 disjoint edges. Okay. So there is a comment which says A D E B C F and I H. So yes, so we see that it is a matching of size 4. So what is the size of maximum matching? 4. Okay. Okay. So yes, Lavanya has raised her hand. So is there a question or you want to give a different matching? Okay. Okay, so this question is done then. So this was about matching. Now we'll look at stable matchings. Now we look at stable matching. So what is this stable matching? First of all, in this, what is the input? So in this input, we have list of men. We have two lists basically. List of men, women, or college, universities, things like and then we have their list with the preferences. And if we have this list with preferences, aim is to find a first stable matching. So now I'll define what is a stable matching. Before defining stable matching, what is a matching? Matching is a 1-1 correspondence between men and women. That means if we, so in this list you can see there are 4 men and 4 women and they have listed down their preferences. So a matching will give us, to each man we have to assign a women, and and we have to assign a different women to each man. That is, no two men can be assigned same women, and all women, and every women should be assigned to some men. So that is what is called the 1-1 correspondence. So one of the examples, and this 1-1 correspondence, and what is a blocking pair? So this is a matching M. Block M size, say, where M1 is assigned W2, M2 is assigned W3, M3 is assigned W1, and M4 is assigned W4. So each woman W1, W2, W3, W4 is assigned to some men. Therefore, we see that this is a matching. Now, what is a blocking pair? So, blocking pair will be a will be a tuple of men and women which is not belonging to the matching, but which is satisfying this property that mi is preferring. So miwj will be a blocking pair if mi prefers wj over the women that it has been assigned, and wj also prefer mi over over the men which she has been assigned. So such a pair will be called a blocking pair, and a stable matching will be a matching if there is no blocking pair of m. Now, now we'll see.
Ma'am, can we say that blocking pair is not a part of a stable matching?
Yes, blocking.
So, instead of finding out whether it is a blocking pair,
Hmm.
it is easy to find stable matching, then see whether this is belongs to that or not.
Yeah, so blocking pair is defined with respect to a matching.
So, ma'am, my question is, if I
Yes.
find stable matching,
Hmm.
and then I will say blocking set is not a part of this,
Hmm.
so then I will say it is a blocking.
No. So see, if you have stable matching, then if you have stable matching, then any other pair other than matching cannot be a blocking pair. That is the definition of stable matching. So initially you are given. So matching is any 1-1 correspondence. So and if you have some random matching, it can have a blocking pair. That means it can have a blocking pair in the sense that there can be a blocking pair with respect to that matching. And if we have a blocking pair with respect to that matching, then that matching is not stable. But if we have a stable matching, then any pair cannot be a blocking pair. So was this your question?
No, finding finding it blocking pair is difficult
Yes, yes.
because then we have to see whether you have to see each pair from the stable matching. So it is always better to find stable matching. Then we say whether this set is a belong to that or not.
Yes, yes, that is yeah, that is true. We are not interested in finding blocking pairs. But if you are, but like we don't have to find blocking. But if you have to say that certain matching is not a, that certain matching is a stable matching, then you have to say that there it has no blocking pair. Then you have to check for every pair that it is cannot be a blocking pair.
Yes, ma'am.
Okay. So I'm just so now to say so to say what is a blocking. So suppose this is a matching. So I have this is a matching. M1 is going to W2, M2 is going to W3, M3 is going to W1, and M4 is going to W4. Now question is M3 W2 and M3 W. So if we look at this pair M3 W2, is it a blocking pair with respect to this matching? So M3 W2. So we see M3 W2. So M3 prefers W2 over W1. But what about W2? W2 also prefers M3 over M3 over the men that she has been assigned. So we see that M3 W2 is a blocking pair because M3 W2 is a blocking pair because M3 in this matching has been assigned W1 but she prefers W2. And similarly, W2 has been assigned M1 but she prefers M3. Therefore, both M3 in this pair M3 W2 both are better off than the person they have been assigned initially. So we see that it is a blocking pair. And since it is a blocking pair, this cannot be a stable matching. But what about M3 W3? Is M3 W3 a blocking pair? What do you think? Is M3 W3 a blocking pair? So we are just understanding the definition of blocking pair. So what in this example is M3W3 a blocking pair?
If we say M3, the first choice is W2. So definitely it is a blocking pair.
No, blocking pairs. M3W3 is a blocking pair. So
Man's preference list W2 is the first preference, na, ma'am. Now
nahi,
here we,
yes, but the definition of blocking pair is not that. Blocking pair definition says that this is my matching. So M3 is assigned W1. M3 W2 M3 W3 will be a blocking pair if M3 so M3 W3. So M3 is preferring W3 over W1. So one thing is there. But W3 we see. What about W3? W3 does not prefer M3 over M2. Therefore, it is not a blocking pair. So for blocking pair, both so if so M3W3 so M3W2 was a blocking pair because in this both were happy with the new assignment. But in M3W3 we see that M3 has been given W1. So if he'll be given W3, he'll be happy. But what about W3? If W3 will be given M3, she won't be happy because she was getting a better preference earlier. So if after this new assignment both are happy, then that is a blocking pair. So M3W3 is not a blocking pair because W3 is not happy in this situation. But M3 W2 is a blocking pair because in this situation M3 is also happy because she is getting a better person and W2 is also happy because she is getting a better person. So in the so if we have a matching, a pair will be a blocking pair if both the people are happy after the assignment. Did you understand? Now, did you understand the definition of blocking pair now? Any confusion?
If we say from M1 male side,
Yes.
M1 is preference is W2.
Yes.
Similarly, M3 is also preferring W2.
Hmm.
So here itself is a dispute is there, na? So that definitely M3 W3 is a what you say uh, blocking pair. What I understand, ma'am, where the situation of conflict is there.
Yes. Okay. Yeah. But but M3W3 is a blocking pair for the reason, this reason. So M3W3 is not a blocking pair. So M3W3 is not a blocking pair. M3W2 is a blocking pair. M3W3 is not a blocking pair because W3 won't be happy when M3 will be assigned to her, because she is already getting a better preference. So M3W3 is not a blocking pair with respect to M, but M3W2 is a blocking pair. This is what, did you understand the definition of block? Did everyone understand the definition of blocking pair?
Yes, ma'am. Yes.
Okay, we'll look at one more example, and then, so now this is another matching in the same example. So we see that M1 is assigned W4, M2 is assigned W3, M3 is assigned W2, and M4 is assigned, so this is W1. M4 is assigned W1. And in the same table we can see, so W1 has been assigned M4, W2 is M3, W3 is M2, W4 is M1. So now the question is, so see, the question is M1 W2 a blocking pair? So M1 will be happy with this assignment because M1 is getting a better option than what it is assigned. But what about W2? Is will W2 be happy getting M1? Is M1 W2 a blocking pair? So there's an answer, no. So okay, in the comments you are saying that, so there's a comments mein there's someone saying that M3W3 is a blocking pair, but M3W3 is not a blocking pair. We discussed that. And now okay. So the question is M1W2 a blocking pair? So for M1W2 to be a blocking pair, both M1 and W2 should be happy with this new choice. So we see that M1 will be happy with this new choice. But W2, in W2 we see that M1 is rating lower than M3. So W2 won't be happy with this new choice. So M1 W2 is therefore, for this reason, is not a blocking pair. What about M4W4? Is M4W4 a blocking pair?
No, man.
No. Why? Why it is not a blocking pair?
W4 is not preferred to
Yes, because
M4.
yes, W4 won't be W4, if we W4 will be assigned M4, M4 is not a better preference than what it has already been assigned. So M4W4 is not a blocking pair. So now does this matching has any blocking pair then? So we see that M1W2 is not a blocking pair, M4W4 is not a blocking pair. So is there, now the question is there a blocking pair for this matching? So this is not a blocking pair. This is also not a blocking
I
pair.
think M2W3, ma'am.
M2W3. But
Yes, ma'am.
M2W3 is already in this matching.
Oh, okay, ma'am.
So you see that. So see the M1 is getting his second preference, M2 is getting first and third. So M1W2 is not a blocking pair, M4W4 is not a blocking pair. So we see that there will be no blocking pairs, because if we look at any other pair other than these two pairs, then we'll be looking on these pairs. But in these assignments, we won't be men won't be happy, because they are already getting their preferences. So M2 is already getting W3, its first preference. So if any other pair with M2, if we take any other women with M2, M2 won't be happy. So M2W1, M2W4, M2W2 cannot be a blocking pair. Similarly, M3W3, M3W1 and M3W4 cannot be a blocking pair, and M4W3 and W2 cannot be a blocking pair. So we see that there can be no blocking pairs in this, with this respect to this matching. Therefore this matching is stable. So does everyone understand three things? First, that why M1 why M1W2 and M4W2 are not a blocking pairs, and why this matching has no other blocking pairs. That is why this matching is stable. Any doubts in this? Any doubts in this question? Anupam, did you understand the blocking pair?
I'm a little bit confused, so I will recall it. Then again, I will study this.
Okay, but I recall the definition, right? So M4, so did you understand why M4W4 is not a blocking pair?
Actually, I lost the concept, so that is why I am confused. So I will come up, ma'am. I
Okay,
will again revise that.
okay, okay. So now let's do some questions then. So now, yes. So first question is this: is AC, BA, CB, DD? So first of all, we have this. So we have these two lists: student list and a university list. So students have given their preferences, and university has also given their preferences. Now, and we are given some two matchings, M1, and there's this another matching, M2. Then we have to say whether these matchings are stable or not. So to say that a matching is stable, that means it should not have any blocking pairs. So first matching is given like this. So we see AC, BA, CB and DD. So this is the first matching, where A is going to C, B is going to A, C is going to B and D is going to D. And in the, if we look at this, so if we look at this, A is going to B here, B is going to C is going to A and D is going to D. So what do you think? Is this a stable matching? So if it is a stable matching, that means if we look at any other pair in this matching, that should not be a blocking pair. Okay. So what? So is the first matching a stable matching? So first of all, any pairs lying here, they cannot be a blocking pairs, because if we look at BD, so these students are these cannot be, these pairs cannot be a, these pairs cannot be a blocking pairs, because they are lower preferences for students. They are already getting, so B is getting A, which is better than D. C is getting B, which is better than both A and D. And D is getting D, which is better than ABC. So none of these pairs can be blocking pairs. So we just need to check that if it is a stable matching or not. We just need to check for these six pairs now. If these six pairs are also not blocking pairs, then we are done. So what do you think? So what is so is AD? So first let's look at AD, AA and AB. Are these blocking pairs? So is AD a blocking pair? Is AD a blocking pair? So if we,
No, no.
no, because A is getting a better option, but little d is not getting a better option. So AD is not a blocking pair. What about AA? Is AA a blocking pair?
Yes, ma'am.
Okay, why AA is a blocking pair?
A is preferred for D, ma'am. Most preference. And then
No, so see, A is assigned C. So so A is assigned C. So if he'll
yes,
be
ma'am. Okay.
assigned university A, it will be better. But if university A is getting capital A, is university A better off? Is university A happy with the new choice? No, because A prefers B over A. So we see that in this A is not happy. So AA cannot, so AA is also not a blocking pair. So does everyone understand why AA is not a blocking pair?
Yes, ma'am.
AA is not blocking pair because little a is going to capital B, and little a does not prefer B over A. So in this scenario, only A is happy, B is not happy. So to say that it is a blocking pair, both both the capital letters and the small letters should be happy. But in this case, only one is getting happy. Therefore, it is not a blocking pair. What about A, B? Is AB a blocking pair? Is A, B a blocking pair? So we see that AB is not also not a blocking pair because
Yes, ma'am.
AB is also not blocking pair because B is getting C, which he doesn't which it is not preferred over A. So we see that these three are not blocking pair. What about BC? BC is also not a blocking pair because little c is getting capital A. So So next we see this is not a blocking pair, this is not a blocking pair, this is not a blocking pair. Then we have to check for BC, BB and CC. Now if we look at BC, C is getting capital A and B is lower in the ranking. So this is also not a blocking pair. And similarly for BB, B is getting C which is better off than B. Therefore BB is also not a blocking pair. And C is also not a blocking pair. Because little c is getting C which he doesn't prefer over capital A. Therefore CC is also not a blocking pair. So in this first matching we see that there are no blocking pairs. Therefore this matching is stable. So is the first question clear to everyone? Why the matching given in 1 is a stable matching? Any doubts in the definition of stable matching or the blocking pair? Okay. If
Why choose A, D, A, A, B
sorry,
as well as B, C, B, B?
yes. So
Why I can choose A, D, A, B?
why you cannot choose BD? You are saying
Eh, yes, ma'am.
yes. So see, you need you. So if you look at BD, if you are looking at any of the matchings which are there, which are basically after the matching they are given. So if you are given BD, then B is not happy with this choice, right? Because B is already getting a better choice, A. So this cannot.
Okay, ma'am.
So if you are choosing anything which is on the which is after these students are not happy. Therefore it is sufficient to check just for the ones which are lying on the left.
Okay, ma'am.
Okay. Okay. Yeah. So now we have the second matching. Now if you look at the second matching, so we see that in this one this is a stable matching. Now if you look at the second matching, this is AC, BB, CD and DA. So now we have to check if it is a stable matching. So we'll check for these. Now okay, so here also if we to ease our condition, D, A is D, uh, B is B, A C. So I am saying that this is not a stable matching. I am telling you the answer. The answer is no. Now you just have to give me a blocking pair. So the matching in B, second matching is not a stable matching. And to show that it is not a stable matching, you have to give a blocking pair. So give a blocking pair in this matching with respect to this matching. So to say that it is not a stable matching, it is sufficient to give a blocking pair. So can you give a blocking pair for this? Okay, so there is one answer. CC. So CC is a blocking pair. So if we look at CC, is it a blocking pair? So if we are looking at CC, so capital C is getting a better choice. But little c is not getting a better choice. So CC is not a blocking pair. Because C is getting A, which is so little c is not happy with this choice, new choice CC. So this is not a blocking pair. So CC won't work. So you have to give something else. CC is won't work. CC is not a blocking pair. It's okay, but you can try. So this has a blocking pair. Try finding a blocking pair.
Can we say DC, capital D and small c is a blocking pair?
No, capital D and small c is not a blocking pair because capital D is assigned A, which is better than C. So capital D won't be happy with this new choice. DC is also not a blocking pair. So right, DC. So does everyone understand why CC and DC is not a blocking pair? So
Uh,
first of all,
capital D, small d is a blocking pair.
capital D, small d. Yes, capital D, small d is a blocking pair because capital D is also getting a better option here and small d is also getting a better option here. So in capital D, small d, D is also happy with this new choice, little d is also happy with this new choice. So yes, it is a blocking pair. And there is one more. So there's one more thing in comments. So Sundar is saying CB. No, okay, sorry. So he is saying CB, capital C, little b. Is capital C, little b a blocking pair? What do you think? Is this answer, is capital C, little b blocking pair? So capital C is happy with university B because earlier he is getting university D,
It,
but his
it is it is not a blocking pair now.
capital C little b. Why is it why it is not a blocking pair? Why it is not a blocking pair? So capital C is getting university B, which is better than university D. Student C. So student C is happy. Now if you look at University B is getting student C, and earlier University B was getting student B. But University B is also preferring student C over B. So University B is also happy with this new choice. So since both student C and university B is happy with this new choice, it is also a blocking pair. And since this matching has a blocking pair, it cannot be stable. So is this clear? Any doubts?
Yes.
Okay. Now, once we know what is stable matching, then we also have an algorithm, Gale-Shapley algorithm, to find a stable matching. So let's look at this. Look at the algorithm. So if we want to find a stable matching, we have this algorithm. First of all, we are given two lists with their preferences. And suppose we want to find, first list is of men and second list is of women. And suppose we want to find suppose we want to find men oriented matching. If we want to find men oriented matching, then what we do with, we'll run this algorithm until all men are engaged. That means all men are paired with some women. So we'll start with first men m1, and then we'll look at the highest preference of men. So suppose that is w. So if w is free, as in it has not been assigned to any other men before, then mw becomes a pair, they becomes engaged. But and so mw becomes a pair and m is not free. Now but if w is already engaged to m prime, then we look at the preferences of w. So if w prefers m over m prime, then we'll mw will get engaged and m prime will be free. M prime will be free. But if w prefers m prime over m, then M remains free and we look at the next women. So this is the algorithm. We'll try to solve solve it with an example. So suppose in this only, if we had this if we have this, okay, we'll come back. Wait. Suppose now we have this. These are the preferences. So we have a list of boys and we have a list of girls, and we also have their preferences. We want to find a stable matching using the Gale-Shapley algorithm when boys are making proposal. So that means we are finding a boys oriented matching. So we'll start with boys. So we'll start with the first boy in the list, which is Adam. So in the first step, and what is the highest, like, what uh, who does Adam prefer the most? Who is the highest preference? Beth. So, and since Beth is in the beginning, Beth is not engaged to anyone, Adam Beth becomes a pair. So we have this Adam Beth becomes a pair. Now, now we look at the second step. So second free man is Bill. Now what is the highest preference for Bill? Who does Bill prefer the most? Bill prefer the most Deanne, and Deanne is free. So Deanne gets engaged. Now now we look at Carl. Now third is Carl. Next free man is Carl. So now if you look at Carl, then Carl, sorry, yes, yes, there is a question.
என்னண்ணா பாக்குற? படிக்கிறேன். படிக்கவே இல்ல, சும்மா பாத்துட்டு இருக்க. ஆமா, ஆன்லைன் கிளாஸ்.
Hello.
போட்டோ எடுத்துக்கிற? போட்டோ இல்ல, அவங்க அடுத்தது ஸ்கிரீன்ஷாட் எடுக்கிறேன். ஐயோ,
Okay. So what about Carl? Who's the preference for Carl? First preference of
Ellen.
Carl. Carl is Beth. But can we assign? So now, since Beth is not free, Beth is already engaged, we'll look at the preferences of Beth. Now, Beth prefers Carl over Adam. Therefore, Carl will get engaged to Beth. And Beth Adam will not be engaged. Because, simply for the reason, because there was a conflict. So Carl was preferring Beth was already engaged to Adam. Then we looked at the preference of Beth. Now since Beth prefers Carl over Adam, then Carl and Beth will be engaged and Adam will be free now. Now at the fourth step, now the next free man is Dan. So now what is the Dan's first preference? Dan's first preference is Amy, and Amy is free. Therefore Dan and Amy will get engaged. Now what about next? Now next is Eric and Beth. So what do you think about Eric and Beth? So now since Beth is already engaged, so now what will happen? So now Beth is already engaged to Carl, and Eric also wants to also wish to propose to Beth. So now we look at the preferences of Beth. Between Eric and Carl, Beth prefers Carl. So Carl will remain engaged and Eric will remain free. So now we'll move to the second preference of Eric. And second preference of Eric is Deanne. So now we'll look at the preferences of Deanne. Eric, so we have this first choice was Eric Beth, which cannot happen. So they cannot be engaged. Now second was, next step is to go look for the next proposal, which is Deanne. But Deanne is already engaged. So if we look at the table of Deanne, Diane is preferring Eric over Bill. Therefore, Eric and Diane will be engaged and Bill will be free. So now the status is this. Carl is engaged to Beth, Dan is engaged to Amy, and Eric is engaged to Diane. But Adam and Bill are free. So now we'll go to Adam. So Adam has already proposed to Beth. So he cannot propose to Beth. So now the next he'll propose to Amy. So what will happen now? So can Adam and Amy be engaged? So can Adam and Amy be engaged? So what do you think? Can Adam and Amy be engaged? Yes, the question is Adam is free. Now do we have to see second choice? Yes, we have to see second choice because first choice already we have seen the first choice. So can Adam and Amy be engaged now? So Amy is already engaged to Dan. Now, since Amy is not free, we'll look at the preference of Amy. So, who does Amy prefer? Amy prefer Adam or Dan? Now, since Amy prefers Adam over Dan, Adam and Amy will get engaged. So, you see, Amy prefers Adam over Dan. So, Adam and Amy will be engaged and Dan will be free now. Adam and Amy will be engaged and Dan will be free now. So now what is the next step? After Adam, who is the free man? Who is the next free man? After Adam, who is the next free man? So we see after Adam, Bill. We have to give Bill. But Bill has already proposed to Diane. So we look at the second preference for Bill. Second preference for Bill is Beth. But Beth is already engaged to Carl. And Beth prefers Carl the most. So Bill and Beth also can't get engaged. Then we'll see at Bill, the next preference is Amy. So what about Bill and Amy? Can Bill Amy be engaged now? So Amy is already engaged. So we look at the preference of Amy. So Amy prefers Adam over Bill. So Amy cannot be engaged either. So now we look at the next preference of Bill, which is Kara. So can Bill and Kara be engaged? Yes, because Kara is free. Now the next free man is Dan. Dan has already proposed to Amy. Then the next preference for Dan is Diane. But Diane is already engaged to Eric. So Dan cannot go with. So okay, now this is the situation. Adam goes to Amy. Beth and Carl are engaged. Eric and Diane are engaged. And Eric and Kara are engaged. And Kara and Bill are engaged. So the next free man is Dan. So the next free man is Dan. So Dan has already proposed to Amy. We cannot look at that. Then we look at this second preference, Diane. But Diane is already engaged to Eric. So we look at the preferences of Diane. So who does Diane prefer, Eric or Dan? Since she prefers Eric over Dan, so Dan and Diane cannot be engaged. Then we look at the next preference for Dan, which is Kara. So can Dan and Kara be engaged? Can Diane and Kara be engaged? So Kara is already engaged to Bill. And since Kara prefers Bill over Dan, we won't change this pairing. So Dan and Kara cannot be engaged. And if we look at Dan and Beth now, Beth is also already engaged and she is getting her first preference. So she doesn't prefer Carl over Dan. So Dan and Beth won't be engaged either. So the last option is Dan and Ellen. So Dan and Ellen. So we see that this is the stable men oriented matching. So does everyone understand this algorithm? Any doubts in this question? Should we do one question like this? One more question like this?
Yes, ma'am.
Okay. Okay. So I'm just okay. So let's look at this question only and try to find a student oriented matching. So first of all, I'll just quickly make this. So we have this. Okay. So now we have to find a student oriented matching. Okay. So we start with first free student. Free student means that who has not been assigned any university yet. So we see that since we are starting this algorithm, A is free. So our first pair will be A. And what is the preference of A? Preference of A is D. So A and D will become the first pair. Now next free student is B. So B has preference C. But now there is a conflict. C has first preference C. But B has already been given C. So what will we do in this situation? So we have already assigned university D to student A and we have assigned university C to student B. Now the next free student is capital C. Next free student is C. So C wants to get admitted to university C. But C has already been assigned to B. So what now in this situation of conflict, what we do is we look at the preferences of university. So B wants to go to university C and C wants to go to university C. But who does university C prefer? Who does university
C.
C prefer?
Small c will prefer capital C.
Yes, C is preferring small c with. So then what will happen? Then B will be free and capital C will be assigned C. So this is this. Now who is the next free student? Who is the next free student?
D
After
with small d. D
D
with
with
small
small.
d.
But now D is already been assigned university A. So what in this situation what we'll do? We'll look at the preferences of university D. So who does D prefer? A or D? Who does university D prefer?
D.
It prefers D. So AD, so D, little d will be the pair and A will become free. Right? So we have this D and A will become free. So who now, since the next free student is A, so who will get, so A has already applied to university D. So we won't look at D. We look at it as second choice. So we look at A, and since since the small a is free, A will be the next pair. And what about B? Then the next free person is B. And since little b is also free, BB will be the next matching. So this is the stable matching. So now does everyone understand this?
Yes, ma'am.
Any doubts? Okay.
So in this stable matching, all other pair,
Hmm.
they are, can we say any other pair is a blocking pair?
No, if it is
Is
a
not a
stable
blocking.
matching, it's not a blocking pair. Yes, we can
Now,
see
so
this.
suppose if I take A, B,
A,
capital A and small b, so is it a blocking pair? No.
no, no, because see, A is already getting university A. So getting university B won't make him happy. So A, B cannot be a blocking pair. For something to be a blocking pair, so suppose some university, so first is student and this is university. So this is a blocking pair if a student is also becoming happy with this new choice and university is also becoming happy with this new choice. But in this case, A little b, student A is not getting happier with this new choice, right? Because he is already getting a university which he prefers over B.
Yes, ma'am.
So you see that any of these cannot be a blocking pair because they are in the lower preferences of students than they are being assigned. So only AD or BC can be a blocking pair. But is AD a blocking pair? Is AD a blocking pair? A little d. It should not be a blocking pair because our Gale-Shapley algorithm is giving us a stable matching. But why AD is not a blocking pair? A is getting a better choice. Why AD is not a blocking pair? A is certainly getting a better choice of university. But little d is getting university D. So A is becoming happy, but D won't be happier. Sorry. Huh. D won't be happier getting student A. Therefore, AD is not a blocking pair. Right? So, so we are getting a, so any confusion in stable matching or blocking pairs?
Can you
No,
please
ma'am.
repeat this example now? What you said? AD. I think AD. It looks to me like it's a blocking pair.
Okay, so see, why AD is not a blocking pair? So we have to, so to say something is a blocking pair, to say something is a blocking pair, A should, so both the first and second should be happier. A should be also happy with this new choice. D should also be happy with this new choice. By happy, I means that they are getting better options than they were getting before. So we see that A is assigned a university A. So if we assign him university D, he will be happy. But what about university D? University D we see has been assigned student D, right? So if we assign to D student A, University D won't be better off. Therefore, it is
Yes,
not
yes.
a blocking pair. Both should be in blocking pair, both should be better off.
Thank you. Thank you.
Okay? Yeah.
Okay, ma'am. Okay.
Yeah. So, okay, we did that. So now, so to see, so this is, let's do this last to see if we have understood stable matchings or not. So I have these three matchings. We have to say whether they are stable matchings or not. So first matching is AY BZ CX. So Y is getting A, Z is getting, huh. So is this matching stable? Is M1 stable? Question. Is M1 stable? What do you think? So if it is stable, that means it does not have any blocking pairs. So what do you think? Is M1 stable? So to say it has a blocking pair, then there should be a pair in which both will be happy with this new choice. So see, in this case, see, all A, B, C are getting their first preferences. So if we consider any pair other than A, Y, B, Z and C, X, A, B or C won't be happy. Suppose if we choose a pair AX, AX won't be better off. A won't be better off with this choice, right? Because A is already getting his first preference. Similarly, so none of these pairs can be a blocking pair. Therefore, it is a stable matching. Because they are already getting their first preferences. So if we took any other pair, they will be, so if we took any other pair, they won't be getting a better preferences. So we see that M1 is a stable matching. Does
A
everyone
comma
agree?
X, ma'am, I have a doubt. A
Yes.
comma X is why it is not a blocking pair?
A comma X.
X. If we take A comma X, na, X prefers
Okay,
A
wait,
first,
sorry,
no?
sorry. Yeah.
Uh,
Uh, it's wait. So there's this A prefers Y. Okay.
uh,
Okay. So this table. Oh, sorry. Shit. Yeah. So A prefers Y, B prefers Z. Okay. So now Y is getting A. So you are saying AX is a blocking pair.
blocking pair. Why it is not a blocking pair then? It's just a,
Okay.
it's
Yeah,
my
yeah, yes.
preference.
Yes,
Yeah, I
yes.
thought
Okay.
A comma X is a blocking pair.
Yes, okay, okay. So yeah, you are right. So I colored the wrong things, that way I was saying. Okay. So wait, you are saying A comma X.
X.
Yeah, it cannot, it is not a blocking pair because
Uh,
A is getting Y, which is a better option. AX is won't make, AX is not making this
okay,
A
but X
happy.
prefers
Okay. So, so see, AX is not a blocking pair. Yeah. AX is not a blocking pair because A is getting Y, right?
A is getting
Y.
Y, but the preference of X when you take X.
Huh. So when you, so when we take the preferences of X, so in for it to be a blocking pair, both should be happier with the new
Ah,
choice.
yeah.
In this, A won't be happy with this new choice, right? Because A prefers Y over X. X might be happy, but
X is happy with B, no, ma'am.
wait, wait. What I am saying is, this is
Ah,
A, B, C. So to say that AX is a blocking pair, so X is assigned, so X is assigned C, uh, Z is assigned B and y is assigned to A. Yeah. So see, if you so AX is not a blocking pair because A is getting Y, which he prefers over X, right? So it cannot be a block. If to say that it is a blocking pair, the new setup should make A also happy, X should also happy. So in this setup, X is happy for sure because because X prefers A over C. But A does not prefer X over what it has been assigned. So AX is not a blocking pair. Do you understand, or is there?
Ah, now I understood.
So now in this case, see, since everyone is getting their first preferences, there can be no blocking pair. Because if we pick any other choice, they won't be happy because they will be getting their second or third preference. In this matching, they are already getting their first preferences, so this cannot be this cannot have any blocking pairs. So is it clear why M1 is a stable matching?
Now it is clear.
Okay.
Yes, yes.
So now what about M2? So let's see what M2 looks like. M2 looks like AX. So now suppose they are getting their second preferences in this CZ and oh, so sorry, first I did M3. So now X is getting A. Huh. So what about this matching? What about this purple matching? M3. Is M3 a stable matching? So we see M1 is a stable matching. Is M3 a stable matching?
Both are getting second preference.
Huh.
It is a stable matching, man. It is a stable matching.
Yes. To say that both are getting their second preference. Yes, you are right. But still, is it a stable matching or not? To say that it is a stable, to say that it is a stable matching, it is not a stable matching. You should be able to give a blocking pair. So if this matching has a blocking pair, then we can say it is not a stable matching. But so you Anupam, you said it is a M3 is a stable matching. Why do you think it is a stable matching?
No, ma'am, it is not a, it is not a stable matching.
Okay, so there are so Vivek is also saying it is not a if it is not a stable matching, then you should be able to give me a blocking pair. So we'll see. So what about AY? Is AY a blocking pair for M3? Is AY a blocking pair for M3?
A prefers Y,
A prefers Y,
Y,
but
but Y prefers B.
hmm. So AY is not a blocking pair, right?
Ah, yes.
What about BZ? Is BZ a blocking pair?
B
BZ is not a blocking pair. B
is
prefers
not a
Z.
blocking pair
B
because B prefers Z, Z prefers
C
C.
over D.
Ah,
Yes.
it is better than
Hmm.
B.
And what about CX? Is CX a blocking pair?
CX. CX.
X also
Yes. Not a blocking pair.
not a blade. So also, and these are the so AY B. So these are not blocking pairs. And similarly, AZ, BX, and CY won't be blocking pairs because they are already getting their second preferences. So
Yes.
so
And we need not check for the third.
what
Yeah.
we not need not check for the her. So we see that M3 is also a stable matching, right? So does
Yes.
everyone agree that M3 is a stable matching?
Yes.
Because we are not able to find any blocking pair, therefore it is a stable matching. So somebody said BY is a blocking pair for M3. So we cannot say BY because BY is already present in M3. So a blocking pair is a pair which is not a part of that matching. So you have to look, so to find a blocking pair, you have to look for all the pairs outside these matching. So now what about M2? So M2 is this AZ BXCY. So what do you think? Is M is M2 a stable matching?
No, madam. It is not stable.
So see, if you are saying it is not stable, then you should be able to give a blocking pair. So in this you see X, Y, Z
If we
are get,
consider,
huh? Yeah.
if we consider AX,
If we consider AX,
X,
so A is getting better off. But is X getting better off?
X getting better on B.
Huh. So AX is not a blocking pair. So we see that AX is not a blocking pair. So we have to check, first of all, these are the, we have to check everything on left. So in this you see, since X, Y, Z are getting their first preferences. X, Y, Z are getting their first preferences. So if we look at any other pair, X, Y, Z won't be happy. So this matching won't have any blocking pair. So this is also a stable matching. Because in this X, Y, Z are getting their first preferences. So if we look at any other pair other than X, B, Y, C, Z, A, X, Y, Z won't be better off.
Ma'am, but we have to see from one side. Now, if we have to see from first matrix,
Hmm.
we see the this Gale-Shapley algorithm is to have a reference either man's side or woman's side.
Yes, yes.
So now, if we are checking from this capital A B C side,
Hmm.
so we have to see from that side whether this is stable or not.
No, no. So I, this question just saying, is this matching stable? So if the question was like if ABC are men and this, if so it is not saying that some oriented stable. So your answer would have been correct if it is has been saying that if this matching
Yes.
is
No, no.
ABC oriented stable.
Yes, yes, yes. So
But this
that
is
is why
just but this
understood,
is general
understood.
stable. So we just
No,
have,
no, they are stable. But if we say from ABC capital side preferences, then it is not, ma'am, stable.
then it is not, because if we'll apply Gale-Shapley algorithm, we'll get the first matching. If we do it from ABC side, right? AYVZCA.
Yes, yes, ma'am. Yes,
But if we are not saying any orientation, and we are generally asking if M2 is stable, then we see, since they are getting their first preferences, any other pair cannot be a blocking pair. Therefore, all these three matchings are stable matching because we cannot find a single blocking pair for these matchings. So is everyone convinced why all these three matchings are stable?
Yes, ma'am.
yes,
Is
ma'am.
there any,
Yes.
by seeing these colors
Hmm.
arranged in a column, the last column, first we see this column,
Hmm.
one A, B, C, and X, Y, Z as a columns.
Hmm. 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 Yes.
You see the yellow color comes at the first and the last one. So
Yes.
if
Yes.
we are able to find such a thing, we can say that it is a stable matching. M1, M2, M3 is stable matching like that. I think it's a very good example now you are giving.
Hmm. Hmm.
Uh, there
Yeah.
is a similarity. We are able to find some similarity.
Yeah.
So
Yes.
is there any graph you can draw to say this is a
Uh, no, this is just a particular example. So in this is basically just showing that. So in a stable matching, so it is not necessary that in a stable, like for a stable matching. So it is like an example which is showing that for a stable matching, it is not necessary that everyone should get their first preferences. Even if everyone is getting their third preferences, then also it is possible that matching is stable.
okay,
Okay.
ma'am.
Yeah.
Very good example. Thank you.
Thank you, ma'am.
Okay. So yeah, that was it. So okay. So I'll end this session if there are no doubts.
Thank you, ma'am.
Okay. Okay.
Thank you, ma'am.
Thank you.